Okay, so looking at this by mathematical induction, let's prove for n equals 1. Okay, so that would mean, now that would just make sure that you realise this is just like a sequence that gives you a relationship between an minus 1 and an minus 2. So if we look at this one here, we actually want to prove true for n is greater or equal to 0. Sorry, so I'll start that again. This here is what we're actually trying to prove, that an equals 1 plus root 2 to the n plus 1 minus root 2 to the n for all n is greater or equal to 0. So it's 1 plus root 2 to the 0 plus 1 minus root 2 to the 0, which is equal to 1 plus 1, which is 2. That's what A0 would equal. So is that true? Now if we look at the top, A0 equals 2. That's what they've got here. Now, we've got A0 equals true. We need to also do it for A1. 1 plus root 2 to the 1 plus 1 minus root 2 to the 1, which will give you, the root 2's will go out, 2. Okay, which is true. Alright, so with this type of induction, with the sequence proof, what we then have to do is we have to assume true so assume true for n equals k. That would mean ak equals 1 plus root 2k plus 1 minus root 2k. And also assume true for k plus 1. Because it's a sequence, and we've got a0 and a1, if you do n equals k and n equals k plus 1, and then prove true for n equals k plus 2, then ak plus 1 will equal 1 plus root 2 k plus 1 plus 1 minus root 2 k plus 1. Okay, and then further we're going to prove for n equals k plus 2. So that's ak plus 2 equals 1 plus root 2 k plus 2 plus 1 minus root 2 k plus 2. Okay. Okay, so the left-hand side is ak plus 2. Now, if you use this sequence here, ak plus 2, an equals 2an minus 1 plus an minus 2. So it's 2a k plus 2 minus 1 plus a k plus 2 minus 2, which is 2a k plus 1 plus a k. So that means that it's 2a k plus 1 plus a k. So it's going to be 2a k plus 1. So a k plus 1 is this here. So that's going to be 1 plus root 2 k plus 1 plus 1 minus root 2 k plus 1 plus then ak, which is this one here, which is 1 plus root 2 k plus 1 minus root 2 k. Alright, so I'm just going to leave the pi's down the bottom and I'm going to see if we can get to it. So what I'm going to do is out of there and out of there, I'm going to take the factor of 1 plus root 2 to the k, and see that will leave 2, that's this 2, times 1 plus root 2 to the 1, because that gives you k plus 1, so k plus 1, plus, this one here is only going to be 1, because I took 1 lot of that out of there, and we go plus, and I'll take out a factor of 1 minus root 2 k, so that would be 2, 1 minus root 2 to the 1, because that would give you k plus 1 when you expanded it, plus 1. Okay, so that means we've got 1 plus root 2 k times, so it's going to be 2 plus 2 root 2 plus the 1, so it's going to be 3 plus 2 root 2 plus 1 minus root 2 to the k, and then that's going to be 2 minus 2 root 2 plus 1, so it's going to be plus, times 3 minus 2 root 2. Okay, now that doesn't quite look like our prize. So this is our prize, 1 plus root 2 to the k plus 2 plus 1 minus root 2 to the k. But if you take the prize, when you go right-hand side, is 1 plus root 2 to the k plus 2 plus 1 minus root 2 to the k plus 2. And then you expand that 1 plus root 2 squared plus 1 minus root 2 to the k, 1 minus root 2 squared. If you take this 1 minus root 2 squared and the 1 plus root 2 squared, and you expand them out, hopefully you'll get 3 plus 2 root 2 and 3 minus 2 root 2. So let's just take that. Let's take the 1 plus root 2 squared. You get 1 plus 2 plus 2 root 2, which is 3 plus 2 root 2. And 1 minus root 2 squared is 1 plus 2 minus 2 root 2, which is 3 minus 2 root 2. So you do get the same thing when you expand that, and then it will equal the left-hand side. Okay, so that means that these can be then replaced with this, and then that equals the left-hand side, then you prove them.